Welcome to Dr. Boxy Teaches Electromagnetism. In the previous clip, we introduced vectors and the algebraic operations we define on them. In this clip, we will introduce components of vectors and we will rewrite the operations we defined previously using those components. So let us get started. We start with a two-dimensional case. We take an x and y coordinate system and we choose some arbitrary vector b. Remember that if b is not starting at the origin, we can just move it around so that it does start at the origin. Once it's there, I draw a line from the end point of b perpendicular to the x-axis, and the point where this line crosses the axis is known as bx, or the x component of b. Similarly, we draw a line from the endpoint of b perpendicular to the y-axis, and it crosses the axis at by, the y component of b. The vector b will often be written as bx, by, as a couple of two numbers. Bx and by are indeed numbers. Bx is in this case positive and by is negative. B itself is an arrow, a vector, and we will often represent it as this couple. Now there's still a second way in which vectors are represented using their components, and that makes use of the unit vectors along the axis. So we define a unit vector x hat pointing in the positive x direction, a unit vector y hat pointing in the positive y direction. Consider now the vector bx times x hat. Remember, bx is a number, x hat is a vector, bx times x hat is a vector, and it points also in the positive x direction because x hat points in that direction and bx is a positive number. And the magnitude of bx x hat is simply the absolute value of bx. The vector bx x hat corresponds to the purple vector I drew. If I look at the vector by times y hat, it points downward. That is because y hat points upward and by is a negative number. Negative numbers flip the arrow around. So y hat points downward, and its magnitude is the absolute value of by. It corresponds to the red arrow in the figure. If we now take the sum of the purple and the red arrow, we simply get the original vector b. This tells us that we can write the vector b as a sum of two vectors, where one of them lies along the x-axis and one of them along the y-axis. What can we do with this? Take some vector b, and here are its components bx and by, and notice that this creates a right triangle. What can we do with it? Well, imagine that I am given the components bx and by, and the question is, what is the length of the vector b itself? Well, if I know the components, I can just apply the Pythagorean theorem to the right triangle here. That gives me that b squared is equal to bx squared plus by squared. Inversely, imagine that I'm given the length of the vector b and the angle alpha between b and the positive x-axis, and I'm asked what are the components of bx and by. Well, I can again look at this same right triangle, but this time look at the cosine and the sine of this angle. The cosine of alpha in a right triangle is the adjacent side divided by the hypotenuse. The adjacent side is bx in this case, and the hypotenuse is b, which tells us that bx can be written as b times the cosine of alpha. And analogously, the sine of alpha is the opposite side divided by the hypotenuse, which is by divided by b. And that tells us that by can be written as b times the sine of alpha. So from the components, we can get to the magnitude of the vector using the Pythagorean theorem, and from the length together with the angle between it and the x-axis, we can calculate the components using the cosine and the sine in the right triangle we get. This is a story in two dimensions. In three dimensions, we get basically the same story. We take a vector b. Its components are bx, by, bz. Bz we get by projecting it directly onto the z-axis. Bx and by can be gotten by first projecting the vector b onto the xy plane, which its projection is the dashed line I drew, and that projection is then projected onto the x and the y axis. We get bx, by, bz. And just like with the unit vectors in the two-dimensional case, we can define unit vectors along the x, y, and z axes, and the vector b can be written as bx times x hat plus by times y hat plus bz times z hat. In order to be able to do some calculations later on, I need the dot product and the vector product of all of these unit vectors. Remember that the dot product of vectors is 0 whenever they are perpendicular to each other. X hat, y hat, and z hat are all perpendicular with respect to each other, which means that the dot product of x hat with y hat, of x hat with z hat, and of y hat with z hat are all 0. Remember also that the dot product of a vector with itself is the square of its length, but the length of all of those unit vectors is by definition 1, meaning that x hat dot x hat is 1, and similarly for y hat and for z hat. So this is what we need for the dot product. What can we say about the cross product? Well, for the cross product, we saw that the cross product of a vector with itself is always 0. That means that all three of these are 0. What can we say about the cross product of the mixed products? So x hat with y hat, for instance. Well, let us look at that. X hat cross y hat is a vector. And what is its magnitude? Well, we saw that the magnitude of a cross product is the magnitude of the first one, the magnitude of x hat, which is just 1, times the magnitude of the second one, which is again 1, times the sine of the angle between them. But the angle between x hat and y hat is 90 degrees, so we get the sine of 90 degrees, which is 1. So we get that the magnitude of x hat times y hat is 1, meaning that x hat cross y hat is itself a unit vector. In which direction does it point? Well, we said that the cross product points always perpendicular to the plane formed by the two vectors. The plane formed by x hat and y hat is the xy plane, so x hat cross y hat points perpendicularly to it, meaning along the z-axis, either upward with the positive z-axis or downward with the negative z-axis. Which one is it? Well, we use the right-hand rule that we discussed in the previous clip, and if you do that, you find that x hat cross y hat points in the positive z direction, and because it is a vector of length 1 pointing in the positive z direction, it simply is equal to z hat. In a completely similar way, we can find that y hat cross z hat is x hat, and similarly that z hat cross x hat equals y hat. We will use these facts now to translate what we saw in the previous clips with the algebraic operations using the components. We take two vectors a and b with their components as given here. What are the components of a plus b? Well, take the two vectors a and b. The way to calculate a plus b was to take the vector a and move b such that it starts at the end point of a. Now the x component of a is the line I drew in red here, and the x component of b is the line I drew in green. The vector a plus b is the blue vector, the one that goes from the starting point of a to the end point of b. Its x component is the blue line I drew below. Notice that the blue line is simply the sum of the red and the green line. This means that the x component of a plus b is simply the x component of a plus the x component of b. The same thing holds, of course, in the y and in the z direction, so we get ay plus by and az plus bz. What can we say about the components of the multiplication of a vector by a scalar? Well, that is simply multiplying each of the components by that scalar. We get lambda ax, lambda ay, and lambda az. What can we say about the magnitude of the vector a? Well, in 2 dimensions, we saw that the magnitude can be calculated using the Pythagorean theorem. The same is true in higher dimensions. The Pythagorean theorem still holds, and that means that also in the 3-dimensional case, we get a, the magnitude of the vector a, by the square root of ax squared plus ay squared plus az squared. Finally, the vector a dotted with x hat with the unit vector in the x direction gives us the x component of the vector a. That is because we saw in the previous clip that multiplying any vector by a unit vector gives us the component of that vector in that direction, but the component of A in the x direction is defined to be AX. These are the components, or the expressions rather, of the operations using the components for the sum, the multiplication with a scalar, and the magnitude. But what about the two kinds of multiplication, the dot product and the cross product? So how do we find an expression for A dot B using the components of A and B? We start by writing both A and B in terms of their components. So A is, for instance, AX x hat plus AY y hat plus AZ z hat. We get the dot product of two sums, and we saw the property of distributivity, meaning that we can work out the brackets. Each of the terms in the left bracket will be dotted with each of the terms on the right. In total, we get 9 terms. I wrote out some of them here. We also saw that whenever we have scalars, some numbers within the dot product, we can just pull them to the front. So the first term becomes AX times BX, which is just numbers, times the dot product of x hat with itself. The second term is AX times BY, both numbers, multiplied with the dot product of x hat with y hat, etc. Now, the dot product of x hat with y hat is 0, as are all the other mixed dot products. So all the terms, except for the ones with x hat themselves, y hat, and z hat, all the other ones are 0. So we're left with just 3 terms. And for each of these, we saw that x hat dot x hat is 1, y hat dot y hat is 1, and z hat dot z hat is 1. So we're left with the prefactors there, meaning ax bx plus ay by plus az bz. So what we see here is that it turns out that the dot product of two vectors A and B, which was defined as the magnitude of A times the magnitude of B times the cosine of the angle between them, can be calculated as well by multiplying the x components of A and B, multiplying the y components of A and B, multiplying the z components of A and B, and adding these 3 numbers together. They give the same result. So this is how to write the dot product in terms of its components. To write A cross B in terms of the components of A and B, we start by writing A and B out in the same way we did on the previous slide, working out the brackets just like we did before, but this time with cross products, once again also pulling all the coefficients to the front. This time, however, the cross product of x with itself is 0, of y hat with itself is 0, and z hat with itself is 0, so we are left with the 6th mixed cross products. The first one that remains is ax by times x hat cross y hat. One of the other ones that remains is ax bz times x hat cross z hat, etc. Now we saw what each of them is. We saw, for instance, that x hat cross y hat is z hat. So the first term that remains is ax by times z hat. I leave it up to you to show that all the other terms give what I wrote here. Now, what we can do is collect all the terms in x hat, collect all the terms in y hat, and collect all the terms in z hat, and what we get is this expression here. This is not a very simple or elegant expression, but it is the expression for the cross product in terms of the components of A and B. There is, however, a simple way to remember this formula. A cross B can be calculated in the following way. We can get it by calculating a determinant of a 3 by 3 matrix, where the first row are the unit vectors along the coordinate axes, the second row are the components of A, and the third row are the components of B. Once again, I leave it up to you to calculate this determinant, but if you do, you will get the expression you find here, which is exactly the expression we found on the previous slide. So this is a simple way to remember how to calculate A cross B. Whenever you have to calculate a cross product, you can do it by working out this determinant. Just as a reminder, the dot product was given in terms of the components by this expression here. What can we do with this? As an exercise, we take a cube of side 1 and we want to know what the angle is between the face diagonals of the cube. So let's take 2 face diagonals. For instance, I take a diagonal along the left face of the cube. I called the diagonal, I made it into a vector and I called it A. And as a second diagonal, I take one at the back of the cube and I call that one B. Now, there are several approaches that you could take to calculate the angle between them alpha. One possible way to do it is to use what we learned about the dot product. We saw that the dot product of two vectors can be calculated in two different ways, either by multiplying a, b, and cosine alpha, or by multiplying the components and adding them. Using this equality, we can isolate the cosine of alpha. The cosine of alpha is then equal to ax bx plus ay by plus az bz divided by a times b. Now all of these components and the magnitude of the vector can be calculated just by looking at the drawing. The vector a, for instance, has a component of 1 along the x-axis, a component of 0 in the y-axis, and a component of 1 in the z-axis. So it's 1, 0, 1. Similarly, b has as components 0, 1, 1. Now using Pythagoras, we can actually calculate the magnitude of each of those vectors, and both of them have a magnitude of square root of 2. I can just plug all of this into the expression for the cosine, and I get that the cosine of alpha is 1/2, meaning that alpha is the arc cosine of 1/2, which is 60 degrees. So this is one way in which we can use our knowledge of vectors to calculate the angle between the phase diagonals of the cube. We now look at something known as the triple product. We start with the cross product of two vectors b and c. Now the cross product itself is a vector. That means that we can take some vector a and dot it with the result of b cross c. The result of this thing is a scalar, and it is known therefore as the scalar triple product. The way to calculate it is, as we will show in the next slide, this determinant. There is also something known as the vector triple product, which is we take the cross product of b and c, that gives us a vector, and then we take some other vector a and we calculate a cross b cross c. And the result of that is a vector. And as we will see in the slide after that, this can be calculated using this expression, which we will look at in one of the following slides. So let's look at each of those triple products separately. In order to calculate the triple product a dot b cross c, we need to multiply the components of the two vectors and add them. So we get ax times the x component of b cross c plus ay times the y component of b cross c plus az times the z component of b cross c. Now the components of b cross c themselves can be calculated using the formula we saw on one of the previous slides, and we get this expression here. I leave it up to you as an exercise to show that this exact same expression can be gotten by multiplying, or rather by working out this determinant. What we see is the dot product a dot b cross c, so the scalar triple product, can be calculated by working out the determinant where the first row is the components of a, the second row is the components of b, and the third row is the components of c. Now, a well-known property of determinants is that switching two rows creates a minus sign. So if I choose, for instance, to switch the first and the third row, the rows of the a's and the c's, I get the same determinant up to a minus sign. If I then choose to switch again two rows, for instance the second and the third row, the net result is two minus signs, and so there is no net change in the determinant. So we get that this is equal to the determinant of the rows of c's, a's, and b's. Basically, I switched two rows. But this, according to what we just saw, is the same as the scalar triple product of c dot a cross b. In exactly the same fashion, we can show that this is equal to b dot c cross a. Note what happened with the order. A, B, C was the original order, a dot b cross c. What we can do is basically shift everything to the right, and when it goes at the end, it comes back to the front. So ABC becomes C comes to the front, the A shifted one place to the right, and the B shifted one place to the right. And we can once again shift it, and we get the B comes to the front, the C goes to the right, and A goes also to the right, and we get this. So as long as we cyclically rotate them in this sense, the scalar triple product remains the same. What is the meaning of the scalar triple product? Well, let's take three vectors a, b, and c. In general, they form a parallelepiped. It's the three-dimensional equivalent of a parallelogram. I want to calculate the volume of this. Now, this is the area of the base times the height. In order to calculate the height, I take a vertical line and the angle between that line and the vector A, I call it alpha. The height is then the projection of A onto that line. Now, what is the area of the base? Well, the base is formed by the two vectors B and C, and we saw that the area of a parallelogram can be gotten by the magnitude of the cross product of the two vectors creating it. So the area of the base is the magnitude of the cross product of B and C. While the height can be calculated because we have a right triangle again, created by the green line, the blue line, and the dotted line on top of it. And in this right triangle, the cosine of alpha is the adjacent side divided by the hypotenuse, which is h divided by a, meaning that the height h can be calculated as a cosine alpha. If I plug all of this into the formula for the volume, I get the area of the base, which is the magnitude of b cross c, times the height, which is a cosine alpha. But that is exactly what a dot b cross c means, because a dot b cross c means the magnitude of a, which is a, times the magnitude of b cross c, which is the magnitude of b cross c, times the cosine of the angle between them. Now, why is the angle between them alpha? Well, remember that b cross c lies perpendicular to the plane formed by b cross c. That is exactly the line perpendicular to it, meaning the vertical line upward. So we indeed find a dot b cross c is the volume of the parallelepiped formed by these three vectors. What can we now say about the vector triple product? Well, the claim is that a cross b cross c is equal to the expression on the right. To show this, what I will do is I will calculate the z component of the left-hand side and the right-hand side and show that they are the same, and leave it up to you to show that the same is true for the x and the y component. So if I look first at the left-hand side, the cross product of two vectors can be calculated by this determinant. The first row is the row of the unit vectors. The second row are the components of the first vector, so that is A. And the third row are the components of the second vector, which is B cross C. Now, if we only look at the Z component of the left-hand side of A cross B cross C, then we only need to take the terms into account that are multiplied in the determinant by Z hat. And those are exactly AX times the Y component of B cross C minus AY times the X component of B cross C. Writing out the components of B cross C, the Y and the X components here, we get this expression. So the Z component of the original expression A cross B cross C is the expression in red at the bottom of the slide. So that is the Z component of the left-hand side. Let us now look at the Z component of the right-hand side. Now, what is that? If we want the Z component, notice that A dot C here is just a number. So we're multiplying this number, which is equal to the whole of this, AXCX plus AYCY plus AZCZ, it's a number, multiplied by the Z component of B, BZ. And similarly for the other term, so A dot B just becomes AXBX plus AYBY plus AZBZ multiplied with the Z component of C. We can now work out these brackets and note that the third and the sixth term cancel each other out. And we can collect the terms with AX together and the terms with AY together, and we get this expression, which is exactly the same expression we found on the previous slide. This shows indeed that at least as far as the Z components go, the two expressions on the top here are equal. And again, I leave it up to you to show that that's true for the other two components. Now that we've discussed the triple products, there are two more topics I want to mention. The first one is the concept of position and displacement vectors. Now, in physics, we will often have situations in which we consider some particle in space which moves around, and we want to be able to describe its position. The way to do that is to say, imagine the particle is at the point that I drew on the graph. What we want to have is a vector r which points from the origin to that point, meaning that if the particle moves around, the vector changes direction and potentially also length in order to keep on following the particle. The components of this vector r will be written as x, y, and z, and so the vector r can be written in terms of the unit vectors as x times x hat plus y times y hat plus z times z hat. The magnitude of r can be calculated using the Pythagorean theorem, and the unit vector in the direction of r, I defined it as r hat, is the vector r divided by its magnitude. Any vector divided by its magnitude gives a unit vector. This unit vector points in the direction of r. And if we plug in the two expressions we found above, we see that that unit vector can be written in terms of its coordinates in the following way. So this is the concept of the position vector. There's also something known as the displacement vector, and that is the following thing. Imagine we have a particle that is at a point with coordinates x, y, z, and it moves to a neighboring point with coordinates x plus delta x, y plus delta y, and z plus delta z. The displacement vector tells us how the change in position is. Now, we usually will look at extremely small displacements, so small that we will consider them infinitely small, infinitesimally small. In that case, instead of writing delta x, delta y, and delta z, we will write them as dx, dy, and dz, but think of them as simply very, very small displacement. The vector displacement is written as dl and is basically a vector whose x component is that small displacement in the x direction, which I call the x, similarly in the y and in the z direction. Throughout this course, infinitesimally small displacement will be written as dl, and they just mean this vector I wrote down here. The final topic I want to cover here is the concept of the separation vector. What this means is the following. In much of what we will do in electricity and magnetism, we will look at charges somewhere in space. These charges will create an electric or a magnetic field, which is something we will discuss in a couple of lectures. And what we want to know is, if we put the particle, the charge, here in this point in space, what is the field it creates at another point in space? So the source point is the point where the particle is actually in, and the field point is the point where I want to know what the field is caused by the source. Now, what we will often need is a vector that goes from the source to the point. To do that, we first say that the field point is at a position r, so the vector pointing from the origin to the position of the field we are interested in will be denoted by r, while the source, the charge that causes the field, will be at a position known as r prime. The vector that goes from the source to the field is r minus r prime. In this course, we will denote it as curly r. The magnitude of curly r is the magnitude of r minus r prime, and the unit vector pointing in the direction of curly r is the vector curly r divided by its magnitude. And we can write all of these using the components. R, or rather curly r, can be written as x minus x prime times x hat, and similarly in the y and z direction. The magnitude and the unit vector can be just filled in using exactly the expressions above. This separation vector is something we will use a lot. This is what I wanted to discuss today using components of vectors. In the next two clips, we will study the calculus of vectors, meaning we will look at derivatives and integrals of vectors. I will see you then.